Yes, today's topic is Königsberg Bridge problem. So Königsberg was a city in the 18th century. This problem was proposed in 18th century. Probably that city was there before the 18th century as well. So the beauty of this city is that it has a river inside the city, and the city is, you can say, the city has four areas. It consists of four land masses. As you can see from the figure, you can see one of the masses is this one of the land mass is this one of the land mass is this one, and one of the land mass is this one. So there are four land masses, and these land masses are connected with the seven bridges. These bridges are shown in the in on with red. These are the bridges. For example, this is the bridge. This okay, actually choose different color. This is the bridge. This is the bridge, third number, and this is fourth, five, six, seven. Okay, so the people of Königsberg commute to different areas of the city by these seven bridges. So uh, mm, they were thinking at that time whether it is possible to go through the whole city. They can walk around the whole city using all the seven bridges exactly once. So this is what we call the Königsberg Bridge problem. Okay. So do you understand the problem? The problem is that can anybody walks through the all parts of the city using the bridges, and he goes to each bridge exactly once. And this is the problem. So first, I'll pose this problem to you people. Eh, what do you think? Uh, is it possible to walk around all the bridges by using once? And if it is possible, let's see which is that path will be. Okay, please go ahead and think about this. Okay, is it possible to have a positive solution of this problem? Do you understand, by the way, do you understand the problem? First, listen. Do you understand the
Yes, sir.
problem? Okay.
Yes, sir. So basically, sir, we have to make sure that we pass the bridge only once, and we have to explore the city,
Yeah,
and uh,
whole city, yes. And you have to
cross all
cross
the one
all the bridges as well, yes.
only.
So if anybody does not understand the problem, he or she can ask. For example, if I try with black color or green color. So this is, for example, somebody starts from here, he moves along this, and then he crosses this bridge, and let's suppose he then goes here, and then this bridge, and then let's suppose he use this bridge, and then this bridge. and now he is stuck here because he has already used these two bridges. So this is not the path which give you the solution. Maybe some other path. Let's suppose if we start from here, goes here, and then here, and then use this path, and then this path or bridge, and then now he has two choices, but the okay, he can go either of the bridge. For example, if you go here, then he comes here, but he does not have any bridge which he previously not used. Or if he move not came here, then again if he came here, then he do not have any bridge that he cannot used before.
Sir, what if he starts from the area at the bottom left?
Okay, let's suppose if you say that if he starts from the bottom left, bottom left is from here, we are saying, let's suppose.
Yeah. Yeah, he
Okay.
starts from here,
Okay.
then goes to the area in the center, then
Okay.
takes the bridge above.
Okay. Now
Comes back to the center,
come back to the center.
takes the bridge below it,
Okay. Now
goes to the bridge on the right,
goes onto the bridge on the right,
uses the bridge in the center.
uses the bridge in the center.
Oh
Now
no, he's stuck again.
now he's stuck again because
Yeah.
there is no bridge which he has not used previously, or she has not used previously. Anybody is using some other method? um, um, this method is that we are trying to make the uh, the paths which satisfy the problem. Anybody is thinking something else? He is trying to solve this problem by some other method. Anybody of you? Or all are doing the same thing? And if somebody is doing this, please elaborate if somebody is doing some other method. Okay, one of the mathematician whose name is, I'll describe some history about this bridge problem, then takes the attention of mathematicians. Uh, it seems from the problem that it is not a problem of mathematics. It is just like a puzzle, but eventually it becomes a problem of mathematics, and it is posed by a mathematician whose name is Euler. He wrote a letter, actually, Leonard. This is Euler, not Euler. He's different from the Euler, but he writes a letter to Euler about this problem, about the solution of this problem. So, I think you know Euler is a famous mathematician. Um, and he's not only doing mathematics, he is doing other like astronomy and optics and different branches of sciences. So he wrote Euler wrote a letter to Euler for the solution of this problem. And in his letter, he gives this picture. He sends this picture to Euler as well, the situation of the Königsberg city. So in this paper, in this letter, he make this picture, and he gave the name of all the bridges. He also tell how the river flows, the direction of the flow of the river. He also mentioned this thing. Now, when Euler get this problem, so he tried the problem, he solved the problem not only for this Königsberg's bridge problem, but for the general case as well. Okay, so in 26th August 1735, he wrote a paper whose title is Solutio Problematics ad Geometrium Situs Pertinentes, mean the solution of a problem relating to geometry of position. यहाँ पर इसने geometry of position की बात की, जो इससे पहले this was not the this was only was this terminology was only named by another mathematician Leibniz, and actually geometry of positions mean this is the geometry um, in which does not involve the quantities like lengths, measures, areas, volumes like this. It only involves the position. And this branch of geometry, I have told you before as well, we call is as a topology. Okay. So इस branch को अब जो हम लोग हैं वो हम we call this problem as a topology. Topology problem. And this is the classical example of what we are discussing in the last week as well. There is a discussion on this thing, that is mathematics invented or discovered. So here, this new branch of mathematics, which we also call topology, and it's some sub branch which is also called graph theory, arise from this problem. Okay, and Euler was the first one who solved this problem in this paper. So he distinguished the problems, two problems from this one problem. And the first thing he do is he make his own picture of the map of Königsberg's. And if you see, he named the land masses with capital letters A, B, C, and D. So he start with this thing, that he named the land masses with the letters. And if you see here, small a, small b, this is small b, this is small c, small d, small e, to name the bridges A, B, C, and so on. These are 7 bridges, so he names A, B, C, D, E, F, G, H, E, F, G, sorry, to name the bridges. So this is the first thing he do with the map, and he do not care of the other informations which Euler gave him, like the name of the bridges, um, the flow of the river. All these, he thinks that these are the irrelevant informations. So the only relevant informations are the land masses and the bridges. So he named the land masses with the letters capital A, B, C, D, and bridges with small a, B, and C. So he proposed two problems. One is he called the Königsberg bridge problem, and the other he called the general problem. So Königsberg problem says that find out whether it is possible to find a path that crosses every bridge of this system exactly once. ये जो system ये इसने बनाया, इस system की बात करें, the system of bridges and areas. And the second problem, which is the general problem, that how one can determine the solution for any kind of system that is any kind of branching of river and any number of bridges. So आपके पास अगर general कोई भी ऐसी तरह का system हो जिसमें there are many areas, there are many bridges, so how can we determine whether we can find a path that crosses every bridge of that system exactly once? Okay, so from here till now, do you understand the general problem and the Königsberg problem? The general problem is the generalization of this particular Königsberg bridge problem. If you have any question or any remark up till now, please. So यहाँ पे जो बहुत do you have any question or any remark?
No, sir.
Okay, very good. So, what are the important aspects of proposing the problem like this? So one of the important aspect is that he introduced two kinds of letters, one for the places and one for the bridges. This is one important aspect of this paper. Nobody solved any problem like this before Eulers. So this is actually the key distinction of the graph theoretic approach. Just at that time, when Euler is proposing the solution, there is no graph theoretic things. There is no graph theory in mathematics. Okay, but this is the key point of the graph theory approach, that there are two types of things or two types of sets. Okay, so first thing he do that he introduced two kinds of letters, one for the land masses, one for the bridges. Second thing, he suppressed all irrelevant informations. He focus only the things, the informations which leads to the solution of the problem. Number three thing, which is very, very important thing, the generalization of the problem. So the generalization of the problem actually shifts the focus from puzzle solving to real mathematical question. Because now this become a proper question that whenever there is some system, there is some branching of
I'm sorry, your voice has cut off.
now you cannot hear me?
We can now.
We can now, but it was.
Okay, sorry. So I repeat my things. I'm mentioning the main points of the solution. We have not seen the solution. We are going to see the solution, but the thing what he do with in order to solve his problem, first the very important aspect is that he introduced the notations thing. He introduced two kinds of letters, the capital letters A, B, C, D, for the land masses, and for the bridges he used small letters. Second very important thing, that he suppressed all irrelevant informations. He only focused on the relevant information. Third very important thing is that he generalized the problem. He do not focus only on solving the Königsberg problem and then stop thinking for the general thing. So he posed, this is not the problem which is posed by Euler. This is the general problem is posed by Euler. So he generalized the problem for any situation. Mean he focused from the puzzle, mean he shift the focus to problem to puzzle solving to mathematical, real mathematical question. Okay, so these are the very important aspects of this of the solution of the Königsberg bridge problem. So it seems that there will be some solutions for the Königsberg bridge problem, but maybe those solutions will not be the solutions in the general case. So let's see. Okay, so first thing, the first method he introduced is he called as the first method. Sorry. As the brute force. So first method he introduced is that tabulating all possible paths. The thing which we are doing, जो हम कर रहे थे वही कि he tabulate all possible paths and check whether one of the paths has this quality that we can cross all the bridges exactly once. So one of the method is the very first method जो हम कर रहे थे is that tabulating all possible methods, and he called this method the brute force method. But Euler rejects this method because it is too tedious and too difficult. अभी तो हमने जैसे 3-4 solutions, 3-4 paths बनाए हैं, but there are so many paths and it is very difficult to check each and every path that whether this satisfy the problem in a positive way or not. And also, for example, if we use this method for the general problem, then it become very difficult to do these things. Okay, so now if this method is not elegant, so he starts to think what can he do to improve the method, or how can he tackle this problem. So now I will ask from you people that, for example, if we do not use this problem, how can we can tackle this problem in some other way. Can anybody have some suggestions? Maybe it will be wrong, but try to give some suggestions.
Sir, can you repeat what you've asked?
My question is that first method he introduced is the brute force method, in which we have to tabulate all possible paths and check whether these paths satisfy our given condition or not. But Euler rejects that method. He says that it is too difficult and too tedious to tabulate all the possible paths for Koenig bridge and as well as for the general problem. So for the giving some other method, what he, for example, this is the good thing that he used the notations. So these notations will help him to solve the problem. So I'm giving you a hint. Let's suppose that if you have these notations, you give the notations to the land masses A, B, C, D, and you give the notation to the bridges A, B, C, small a, B, C, D, E. So there is one crucial notation he used after this thing, after using this first method, after rejecting the first method. He tried to, because here he give two types of structures, one giving you the land masses and the other giving you bridges. So he tried to connect them, the two different kind of things, into one. So think about it and tell me what might be possible to connect one of these structures with others.
I'm not sure if this is what you're referring to, but if you draw 4 points A, B, C, D, and draw lines between them, connecting them with the labels of bridges, is that what you mean?
No. This is what we are doing in graph theory. Okay, so I'm not going to the graph theory part. I will go at the end. So let's assume that you are in a situation of doing the problem, and you think about this thing that let's label the land masses with the capital letters, and you label also the bridges with the small letters. I'm saying that, can you think, is there any relation between these two type of labels? Can you think, or can you propose some relation between these two, or one can dependent on other, or the other is dependent on the first one? Not necessarily dependent, but some relation.
You could do A little dc, which means like A connects C through D.
Yes, but what we are saying, Ryan, please repeat. A D C. Okay, A D C. Okay,
Yes.
okay. So what I understand is that you denote the, mm, if one person starts from A and go to C by using the bridge D, you can write this thing like ADC. Am I right?
Yes.
Okay, very good, very good. And similarly, for example, if he use C to A and then he use some other, let's suppose A, and then it comes to A again. Okay, this is one method. How can we simplify this more? So in other words, you are actually denote the whole journey of a person, the whole walk of the person. Somebody is walking around these bridges. So let's suppose, for example, if I write this, so he walks from A to C using the bridge D, and then C to A using the bridge small a. I think it is small a here. Okay, so how can you more reduce this thing? If he wants to use only one, so if somebody wants to use only one letter,
A, because the person ends up at A again from going to A.
so please rhyme again, बताइएगा to start with
This
A.
this person ends up where they started, so you could just write A possibly, but that might be a bit ambiguous, so you can write A
Yes,
D.
yes, because this does not tell. Let's suppose, for example, he goes to from bridge B to B, and then from bridge I to D, and then bridge C to A. So is it the same A because he start from A and then come back to A? So this is not giving
Hmm.
the
You
it
don't
doesn't
need
match.
a C if you can just write A D A.
A D A. You are saying this thing or something else?
No, A D
Small letters or the
small
big letters?
sorry, A little d
A little B.
little d.
Okay, D.
This little a big A.
Here you also use two letters. I want some, let's suppose, for example, if I want only the capital letters.
ACA.
ACA, yes, this is good. ACA, ACA, very good. So ignore which bridge a person use. He goes from A to C and then comes back C to A. Okay, so ignore this the bridge. Which bridge? For example, he can go from A to C by using first the bridge A and then come back using D. Or for example, if he goes from A to D, and so we know that these are two different ways of doing this journey from A to C and then C to A. But if we can represent it by one letter, this is a good thing. So Eulers do this thing, that he use the notation, this notation um, uh, for any walk, you can say, for any walk or for any path. So for example, if we have 7 bridges, let's suppose, and if it has a positive solution, then what do you think, how many letters is used to represent that walk? जी, anybody else, please बाकी भी contribute करें if you're understanding. Zoya, do you understand what I'm saying? The last thing, that if, for example, somebody is traveling from A, let's say starts to walk from A and he moves to C and using any path, maybe D or A, and then come back to from the other bridge to A, then I write this walk as ACA. Okay. So for example, now this we use three letters to denote this walk. So now my question is, if somebody, we still do not know whether the solution of this bridge problem exists or not. Let's suppose there is a solution, then and he used all the seven bridges exactly once, then what do you think? How many capital letters? How many letters will be used to represent all the journey, all the walk?
8.
Yes, good. Eight. We use eight, whatever it will be, but you use eight. And in general, if there is a general problem, then how many you use? For example, if there are n bridges,
1 plus n.
1 plus n. Okay, so that's very important point, and we use this point for the second thing. So the very important uh, innovation, or you can say the introduction of notation thing in for this problem, that he used this thing, that he used only the capital letters to, or you can say the whole journey, he उसको उसने एक mathematical form कह लें या एक symbolic form दे दिए. So Euler gives the symbolic form to the journey made by any person. Two bridges. Okay, so you everybody understand this thing, that for example he goes from A to B using any of the bridge, then he write that A like AB, and if he go back to A, then ABA, and if he goes, let's suppose he go to D using some bridge, then it will be written like ABD. Okay, so um, this is the uh, this represents the journey of a person, or the walk of a person, which starts from A to B and then B to D. Okay, clear? And this is this notational shift um, um, is the graph theory thing, because in graph theory, uh, or in a modern graph theory, you represents the two things, and you say that one thing is the, you can express the one thing in terms of the other thing as well. So मैं जरा थोड़ा modern graph theory भी साथ साथ लेके चलते हैं. So in a modern graph theory, इस तरह की जो भी situation है, we call it as a graph. Okay, this graph is different from which you have studied in calculus, um, or maybe in the real calculus course about the graphs of the functions. So this is different from that graph. This is a graph is represented by the set of vertices V and a set of edges P, represented by pairs of vertices. Mean E is a subset of V square. Okay, so graph, you can represent a graph by a set of vertices, and you denote it by V, that set, and the set of edges, which you say that it is, these are the pair of vertices. So you represent the edges by some vertices, okay, as a pair of vertices. Okay, so this is so-called graph. And if, for example, if you've denoted, so you denote the vertices by points, you denote the edges between them by straight line or by curve, anything what you like. For example, if by let's suppose like this. So here you can denote it by A. This is A, B, C, D, E, and actually the small, let's suppose this is small a, this is small b, these are the edges, small letters are edges, and you can represent this a is actually a comma b, or you can also write it as a b, and here b is the pair bc, or you can write it like bc, and so on. Okay, so this is the definition of a graph. Abstract definition is that it is a set of vertices and another set of edges, which is actually the pair of vertices. And geometrically, or you can say, you can in plane or in space, you can draw the graph by taking as points the set of vertices, by drawing the set of vertices as the elements of the set of vertices as the points, and the edges as a line segment or some curve between the vertices. For example, here AB is an edge, and so you join A with B, and BC is an edge, and we join B with C. Okay, so this is the modern graph theory thing, which Eulers do, and not like this, but he do not make any graph, but he actually do these things by introducing the the bridges as as denote the bridges as, let's suppose if we have a bridge from A to B, we write it as AB. Okay. So he actually relate two structurally related kind of objects. Okay, the edges, the areas or the land masses, and the bridges. Okay, so they are no longer two separate of labels, but only have one, because the other are in terms of the first ones. So this is the idea, basic idea, and which is a very important idea, which leads to the solution of of the the problem. Okay, the idea of denoting the the journey or the walk through by a symbolic notation. Okay, so now we also see that now we're going towards the solution, as we see that if um, somebody is walking through all bridges using all bridges only once, so if there are n bridges, so there we must need n plus 1 letters to describe that walk or that journey. Okay, so first he gives the first method he gives to to solve the Königsberg's problem, and then in the second he will give the solution to the general problem. Okay, so let's do let's see how he solved the Königsberg's bridge problem. Okay, so first thing is that if we want to use every bridge in calling words exactly once the string of letters has to consist of 8. The string has to consist of 8 letters. Okay. So हमारे केस में 7 bridges हैं. So we must have to use um, the 8 letters. So how many letters is we are using? We are using 4 letters: A, B, C, D. So we actually need to see how many times the letter A used, how many times the letter B used, how many times the letter C used, and how many times the letter D used. If somebody tries to go through all the bridges. Okay. So here we denote the number of bridges connected to an area. Denote the number of bridges connected to an area by, let's suppose I name the area by X and area X by MX. Okay, so he denote the number of bridges connected to an area by MX. For example, we have in A, the number of bridges connected by A is 1, the bridge A, that bridge D, the bridge B, the bridge C, and the bridge E. So there are how many bridges connected to A?
5.
5. So we denote it by, let's suppose if I have to denote MA, then MA is actually number 5. Okay. And similarly, what about C? How many bridges are connected with C?
3.
3. And how many bridges with D?
3.
3. And also with B, we have 3. So we have 4. And just represent this. So we have MA is equals to 5, and all others FB is equals to MC is equals to MD. All these numbers are 3. Okay, so we denote this. Okay, so general observation about this number MP, because this number MX can be positive, sorry, it can be odd and it can be even. So let's suppose that if a number MP is odd, then tell, for example, if one of the letters, one of the area has connected with odd number of bridges, then what do you think, how many times that uh, letter will appear in the string? So I repeat my question. For example, we have an area and I call it by P, a landmass by P, and we have odd number of bridges connected to P. Then what do you think? Let's suppose if it is 3, let's suppose P is 3, the MP is 3, which is an odd number. So how many times P will appear in the string? The string
Twice.
which represents the whole journey.
2 times.
2 times. Yes, good. How you get this thing? For example, if you have an area, let's suppose this is an area which is P, and you have 3 bridges, and let's suppose you go and somebody's went and then come back, and then let's suppose here we go somewhere and then come back. So how many times he will the letter P used?
First, you will come into P,
Yes.
and that will be one time. Then you will leave P, and then you will have to enter again for the third bridge,
Yes.
which
Yes.
is the second time.
Yeah. Very good. So when you enter the P, or let's in both cases, for example, if you start from P, there is a two things here. One thing is that do you start your journey from P, and do you start your journey from somewhere else? So let's suppose if somebody starts its journey from P, and there are three bridges which is connected by P. So somebody use the bridge, the first bridge. Okay, so P will comes in the string, and then he come back again after some time. Then P will comes, and then he goes from the other bridge, because we have to use the bridge once. Okay, so and then he goes to the third time. So he only the letter will comes only twice. Similarly, if we have five, let's suppose if we have five, then how many times do you think he will the letter comes?
3 times.
Yes, three times. Because for example, if he go again this, and then he come back again use P, and then he use the other bridge. So three times the letter will come. So generally, how will you represent this thing? So if, for example, the MP is odd, then P appears how many times in the string?
MP minus 1 over 2 plus 1.
Then P will occur MP plus 1 over 2. Okay, not minus 1, and P plus 1 divided by 2. For example, here, if it is 3, then 3 plus 1, 4 divided by 2, this is 2. It is 5, then 5 plus 1, 6 divided by 2, which is 3. Okay, so everybody understand this thing, that if the number of bridges connected to some area is odd, then the P will occur MP plus 1 over 2 times in the string. Everybody get this thing? So let's use this thing in the Königsberg bridge problem, because every NA is odd, MB is odd, MC is odd, and D is odd. So what do you think? What will be, how many times will A occur? How many times in a string A occur?
3 times.
It will occur three times. How many times B will comes in the string?
2 times.
Two times. C also two times, and D also two times. So the string will be, if they used A, B, C, D once, so the string consists of 3 plus 2, 5 plus 2, 7 plus 9 letters. But what we get from the previous is that since there are only 7 bridges, so if somebody is going through each string exactly once, the string must be consist of 8 letters. But the situation tells us that there will be 9 letters. So this is a contradiction. And this contradiction leads to the negative answer of the problem, that there does not exist any such path. ऐसा कोई path आपके पास exist नहीं करता. Do you get the point? Everybody get the point? The solution of the Königsberg bridge problem. If you have
Yes.
questions, please ask. This is a very good um, solution. This is a solution which is given by Euler. G. Anybody? No questions? Okay. So if you have no question, let's move forward. Let's go to the, there is something in the chat. Okay, I'll repeat the whole argument again. So the first thing is that the notation thing. We denote the walk or the whole journey by capital letters. For example, somebody moves from A to go to the area C, and then he goes to B, whichever he used the bridge. So we write it like this: A, C, D. Okay, or A, B, D represents that he moves from A to B by any bridge, and then B to D by some other bridge. So if this means that if somebody used all the bridges exactly once, then there are 8 letters should be used to describe that journey. Okay, वो बताने के लिए आपको 8 letters require होंगे. And we also use this thing or observe this thing that if there are and first we denote this number MP, which tells the number of bridges connected to an area P. If this number is odd, then how many times that string occurs? It will occur MP plus 1 divided by 2 times. Okay, so since A is connected by 5 bridges, so this means that A will be appear 3 times in that string, the string which tells us the journey of a person. B will occurs 2 times, C will occurs 2 times, and D will occurs 2 times. So if A is occur 3 times, B 2 times, C 2 times, D 2 times, then it means that journey will be described by using 9 letters. But previously we said that it should be consisting of 8 letters. That journey should be consist of 8 letters. So this is a contradiction. This means that it is not possible to go through all the bridges by using the bridge only once. Okay, so the solution of this problem is negative, that there is no such path. Okay, next, Euler extend this, because here he also only used this thing that if MP is odd. But what about if MP is not odd, if it is even? And what about if there is a general situation? Okay, so in general situation we can have any number of bridges and any number of connected areas. Okay, so now in the next step we extend this system with the even areas. Extend the method to systems with even areas. ऐसे सिस्टम जिसमें इवन एरियाज भी हैं. सो अब आपको ये पता चल गया कि ऑड एरियाज में कैसे देखना है, होता आपको पता चल गया. लेकिन अगर ऐसा आपके पास सिस्टम है, if you have a system in which you have even areas as well as odd areas, then how can you solve this problem? So for the case of even number of bridges, there are two possibilities. Okay? So if an area has an even number of bridges, there are two possibilities. Let's explore both. There are two possibilities. First possibility. Let's suppose Q. If Q is the starting point of the, here it matters whether you are starting from the point which has even number of bridges or whether you are not starting from there. So for example, if you are starting your trip from a point Q which has even number of bridges connected, and Q is even. Okay, now tell me then how many times the letter Q will occur in the string. You remember you have to use only one.
Twice, and you will end at Q.
Twice. Twice of what? Twice of MQ. Okay, you have some bridges from Q, and Q has even number of. Let's start with two, only two. You are starting your journey from Q. So how many letters will be used then? If
It's three
there are
times.
two bridges.
No,
So Q in the start, and then you go back, and then you come Q. So how you're saying? You're saying three times or four times?
twice.
Twice. It will be twice. So if we have only two bridges, then we have two times. Okay. Let's see what about in four. So if you have four bridges from Q and you start your journey from Q, so then one, you come back two, go out, and then come back three. Are you getting my point? So in the start you have Q, you go and travel and then come back and use Q. Okay, and then gets to some other bridge and then come back to. So how many times? If you have four, then you have three times. When you have two, then you use two Qs. When you have four bridges, so then you use three. Let's suppose if you have six bridges, now tell me how many times. And you are starting your trip from the point Q. How many letters will be used?
Four.
Then it will be used four. Yes, you're right. Q, 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 four. Because you start from here, one Q, and then go back, then the second Q, come again, third, again, come out, and then four. Okay, can you people see my arrow? The arrow, the cursor, or not? I think you will not see. Okay, let's start from here. So Q, when you come here, out, and then you again use the second Q, you are here, and then go here. And then when you are starting from here, then you use the third one. You will here, and then when you here, you will use. So 1, 2, 3, 4. So four times you use the letter Q. So generally, if you have two, then you are using two. You have four, you are using three. When you have six, you are using four. Then what do you think? What will be that number? If you have MQ,
MQ
number
over 2 plus 1.
MQ over 2 plus 1. Good. MQ over 2 plus 1. So this is the case when you start the journey from Q. But what happens if you do not start your journey from Q? You are starting your journey from some other point. Let's suppose R is another point with the even number of bridges, but which is not the starting point. If R is not the starting point,
I think it will be MQ over 2.
and MR is bigger, then the letter R will occur. So you are saying MR by 2. So you divide it by 2.
Yes.
Okay, let's see for this case. Remove all these Q's. You have 6 and you are starting your journey not from Q but from somewhere else. Okay, so let's start your journey from somewhere else, and you come to first Q here, and then you goes out, and then again you have Q when you're entering to the bridge, and then you go out, and then you're entering the bridge, and then you go out. So there are 1, 2, 3, 4, 6 bridges, and then in how many times the letter used? It used 3 times. Yes, you're right. This is MR by 2. You can see for 4 and 2 as well. Okay. So let's put these all three. Now we have all the situations. First situation is that we have all the situations. Number one, if P has odd, you can call odd area and even area. Odd area if there are odd number of bridges attached, even area if there are even number of bridges. So P, let's suppose P is odd, then we see that it has how many times? MP plus 1 divided by 2. If you have even number of bridges attached to some point and you are starting the journey from that point, then you have MQ by 2 plus 1 times the letters occur. And if R is not the starting point and MR is even, then the letter R will occur MR by 2. Okay, so now let's collect all these things and let's try to solve the general problem. Okay. We can call this intermediate method. Euler use this as an intermediate method. So what is intermediate method? So intermediate method is that if n is the number of um, bridges, total number of bridges in the system, length of the string representing, I'm using for this special walk or path as Euler's path after the name of Euler. So representing Euler path. Euler path is the path in which we are using only once the bridges only once. Okay. So this will be n plus 1. Okay. So we write P for areas with an odd number of MP, Q for areas with even MP and Q, and where we start R for areas with again an even number MR, MP and QMR telling us the number of connected big bridges where we do not start. Okay. So we denote all the areas with P, which has odd MPs. We denote all the areas with even MP, MQ, where we start, and all the areas by R, which have even MRs, but we do not start from there. Okay, so जो अभी हमने चीजें देखी उसके मुताबिक हमारे पास ये we get the following equation. So the total number of Euler paths is n plus 1. If somebody has the get the Euler path, so and it have areas in which we have odd connected bridges, we have even connected bridges, we have the bridges even with different starting points. Okay, so the equation becomes sum all the letters with given areas, sum all the letters with, sorry, this is odd areas. Okay, these are odd areas का sum. Sum all the areas with even areas where we do not start them. So that these are NQ by 2. And the last one is NQ by 2. Oh, sorry, this is an R. We denote it by R. NQ by 2 plus 1. This should be equals to, ये number किसके बराबर होना चाहिए? In order to have the Euler path, this number should be equals to n plus 1. Okay, these are even not started, even started. So हमारे पास सिर्फ एक ही होगा ना, जब हम जहाँ से स्टार्ट कर रहे हैं वो तो सिर्फ एक ही होगा, इसलिए यहाँ पर समेशन नहीं आया, सिर्फ एक ही आपके पास ऐसा एरिया होगा जहाँ से आप स्टार्ट कर रहे हैं. सो उस एरिया का जो आपके पास वो कितनी दफा वो लेटर Q जो है वो रिप्रेजेंट होगा, इट विल बी NQ by 2 plus 1. सो इन सब लेटर्स को ऐड करें, सो नंबर ऑफ लेटर्स विल बी इक्वल्स टू n plus 1 होना चाहिए. सो इन अदर वर्ड्स आप ये कह रहे हैं कि ऑयलर पाथ तब एग्जिस्ट करेगा अगर ये equality satisfy होगी. So actually this gives us the necessary condition. This equality gives the necessary condition for the existence of an Euler path. Do you understand?
Yes.
For the existence. Matlab, if this left hand side is not equals to right hand side, we say that no Euler path exists. So no Euler path exists if equality is violated. Okay. So Euler gives two conditions. जो Euler main उसका theorem था, he gives two conditions to so that the path will be an Euler path. So थोड़ा सा और इस पे इनको गौर करते हैं इन चीजों पे. So we will get these two conditions. First thing, the number of odd areas has to be even. पहली चीज ये कि नंबर ऑफ ऑड एरियाज को इवन होना चाहिए. क्यों? First thing is that this is just which is a general thing, because summing up the number of bridges connected to all areas counts every bridge in the system twice. Are you getting this thing? मैं लिख लूं पहले फिर इसको हम बात कर लेते हैं. Summing up the number of bridges connected to all areas counts every bridge in the system twice. Okay. So if you count, yes, if you sum all the bridges which are connected to all areas, so the count will be because in the system every bridge will be counts twice, so that's why the number of odd areas has to be even. For example, if you multiply this equation number 1, इसको elaborate थोड़ा सा इस तरह भी कर लेते हैं. Okay, for example, if you multiply this equation, let's I call it equation as equation number 1. So if you multiply this equation by 2, what will you get? You will get summation mp plus 1 plus it is p summation mr plus mq plus 2, and this is equals to 2n plus 2. Now what is this 2n?
Number of bridges.
Number of all bridges connected with in the system. Okay, so let's suppose you can say that this is equals to mx. This is the number of bridges on bridges. You denote it by mx or summation m, so all. सो आपकी इक्वेशन ये होगी, लेफ्ट हैंड साइड पर आपके पास क्या आ रहा है, सम ऑफ ऑल ब्रिजेस कनेक्टेड बाय द ऑड एरियाज प्लस 1 plus sum of all connected bridges, number of bridges connected with even areas, and plus the starting one with an even plus 2, that should be equals to 2n plus 2. Okay, so equality जो है वो किस किस केस में होल्ड करेगी? So equality will be holds in the following two cases. इसकी जो equality of, we call it equation number 2, equality of equation 2 holds in the following case. Okay, so what are those cases? What do you think? Number one. For example, if I say that there is no odd area, you do not have any odd area, then this equality holds, because number of सिर्फ हमारे पास सिर्फ we have only even areas, and there is from 1 you have started, and if you started from q, then the number of bridges to all areas will be sum of all mr's plus mq, and plus 2 here, so plus 2 will be equate with it, and this thing will be equals to 2m in that case. Okay, so the first one is no odd areas at all. So you will get the one solution to for the Euler path, that you will have the Euler path if there is no odd area. कोई भी आपके पास area odd नहीं है. In each area, the number of bridges connected are even. Okay, you understand? Because if there are no odd areas, this sum becomes 0. This becomes 0. This becomes 2n. This is plus 2, so 2n plus 2. On the right hand side, you have 2n plus 2. Okay. Now, what about the second case? There is one more case. If there are two odd areas, so दूसरी आपके पास तब हो सकता है कि दो odd areas हो, and we have to start in one of them. हमारे पास दो एरियाज हो और हमें उनमें से ही किसी दो ऑड एरियाज हो और उन्हीं में से किसी एक से स्टार्ट भी करना है जब लेट्स सपोज हम पहली इस बात को लेते हैं कि हम वहां से स्टार्ट नहीं करते, हम ऑड एरिया से स्टार्ट करने के बजाय इवन एरिया से स्टार्ट करते हैं. तो प्रॉब्लम क्या है? प्रॉब्लम ये आएगा, यू हैव दिस plus 2 mq plus 2, and you have you are getting from here the, because you have two odd areas, when you have two odd areas and each odd area giving mp plus 1, so mp plus 1 mp, so you have 1 plus 1 2 here as well. So summation mps, we have two times the odd numbers. Let's say we call it we call it mp1 plus 1, and the other is mp2 plus 1. Then this is summation mr, and then you have mq, and then you plus 2. So you have plus 2, you have plus 1, you have plus 1, you have 4 here on the left hand side with mq plus summation mr, mp1 plus mp2, which is equals to 2n. So you have on the left 2n plus 4, and on the right you have 2n plus 2. So you get a difference of 2. Are you getting my point? If we do not start with one of the odd areas, so then this comes, mq plus will come, because this is where we start. This is the number of bridges, sorry, number of number of alphabets used in the string. So this will be MQ plus 2 because we are multiplying by 2 as well in the equation number 1. Okay, so we will get 4 on the left, and 4 more than the total number of bridges, and here we have 2. What about if you have 4 odd areas or 6 odd areas? We first note this thing that number of odd areas has to be 1. आपके पास हमेशा number of odd areas जो होंगे वो even होंगे. So what about if you have 4 odd areas? Do we get the equality or not? This is the question for you people. If we have 4 odd areas, do we get the equality, the equation number 2 equality or not?
No,
Reason?
because then you will have a +4 from the MP plus 1.
Yeah, you're right. For example, you have 4 odd areas and you have start from the odd area. Okay, then this does not happen. This is 0. But because since you have 4 odd areas, so MP plus 1, MP plus 1. So let's go P1, P2, P3, P4. So from each ones you will get here 4, and here you have 2. So again you get a difference of 2. And similarly, if you have 6 and 8 and so on. So this equality holds only if there is no odd area, or if it has 2 odd areas. So at max, how many areas you must have? At max, the system has 2 odd areas. Okay, it is not possible that you have 1 odd area, but it is you have 2 odd areas. So Euler's theorem is the original theorem, Euler's original theorem. I'm saying original because what he proposed in his paper. There is one version of Euler theorem in terms of graph theory, but this is what he proposes in his paper. He says that Euler path exists only if A, the valence of all areas is even, mean there is no odd area. Number B, the valence of exactly 2 areas is odd, and we start the journey from one of them. What do you think if okay, I tell you, for example, if he starts its journey from one of the odd area, then he or she ends its journey from the on the other area. Okay, so this is the condition Euler gives, that the solution of the general problem will exist only if the number of all areas is even. तमाम areas की जो valence है, valence mean the number of connected bridges is even, or the number of connected bridges, or the valence of exactly valence, I'm calling it MP or MQ, of exactly 2 areas is odd, and we start the journey from them. This is what Euler's give the solution. So in the last, I want to go through quickly the version of this problem in the modern graph theory. In the modern graph theory, this Königsberg's modern graph theory. So in modern graph theory, the Königsberg's bridge will be represented by the following graph. It has 4 vertices, A, B, C, D, and each bridge gives you an edge. We have, let's suppose from A to B, we have two bridges, so we connect by two edges from B to D, A to D, and C to D. Okay. This is Königsberg graph. You can call it the Königsberg graph. So the theorem, or you can say what will be the version of the solution, that if you have a, do you have a path from so that you can go through all vertices by using only once each edge. Okay. So, in order to, okay, I'll just give you the theorem and then I'll tell you the the terms in it. The theorem says that a finite connected graph admits an Euler path if and only if there are at most two vertices with odd degree. So just a minute, I'll tell you the terminologies in this theorem, and then you will understand this theorem. So first terminology is finite. So finite means we have the number of vertices is finite. Okay. The second thing is connected graph. So connected graph, before connected graph, I must need to tell you path. What is the, how to define a path in the graph theory, in graphs. Okay, and what is Euler path then? So path is a path in a graph is a sequence of vertices in the graph with each pair of vertices connected by an edge. Okay, so path, for example, if I take a path from, let's suppose I call from C and D, I go from this edge and then D to B. So this is one path, C to D, C, D, B. Okay, so is a sequence of vertices in a graph with each pair of vertices connected by an edge. Okay, second definition here, path के बाद आपके पास आ जाएगा connected graph. So a graph is connected if any pair of vertices admit a path from one to another. Okay, so connected graph, this the Königsberg graph is an example of the connected graph in which every two pair of vertices can have a path. Let's suppose from A to C, you can come from A to B and then B to C. Let's suppose you have A to D is AD, and for example, you have B to C, then you have B to C. So every pair of paths, every pair of vertices has a path. So that's why this is a connected graph. So a graph is connected if there is a path for any pair of vertices. One more important thing is degree. Degree of the graph is the number of, not the graph, the degree of the vertex. Definition is the degree of vertex. So degree of vertex is the number of times it occurs as the endpoint of an edge. For example, here A, the degree of A is how many vertices, how many, it is endpoint of how many edges. It is the, let's go from B to A, this A1, this is 2, and this is 3. So the degree of A is 3. The degree of B is 5. The degree of C is 3, and the degree of D is also 3. Okay. So the last definition is Euler path. So Euler path is the path in which every edge occurs at once at a time, not more than once. Okay. So Euler path is a path that uses every edge exactly once. Okay. So this is the thing. Um, One thing, if you notice the theorem again, now maybe you understand that a finite connected graph admits an Euler path if and only there are at most two vertices with odd degree. हमारे पास ज्यादा से ज्यादा दो vertices ऐसे हों जिनकी डिग्री जो है वो odd हो. And if you notice this thing, the Euler gives only the necessary condition of the Euler path. Here we are giving the necessary as well as the sufficient condition in this graph theory case. This was not proved the other way around, is not proved by Euler. This is proved by some other mathematician. I forget the name. But after 150 years of Euler gave the solution. So this is how you interpret the problem in the graph theory as Euler path, the existence of Euler path. And the theorem says that whenever you have a finite connected graph, okay, if you do not have the finite connected graph, then never you get an Euler path, because you cannot go from one connected component of the graph to another component of the graph, because there is no path which connects the two components. So that's why this theorem is only hold, or this situation only holds in the connected graphs. So finite connected graph admits an Euler path if and only if there are at most two vertices with odd degree. Okay, do you have any questions? I take a very mathematical point of view of this Königsberg's bridge problem, because I was seeing that there are so many videos in the YouTube from where you can get the idea what's the Königsberg bridge problem and what is the solution. Most of them translate the problem in the graph theory and then explain the proof of this theorem, this one. But I was thinking that it will be interesting for you people to think, to see how Euler's proved the theorem, the original problem and the general problem as well, and how the people invent different mathematical ideas or discover mathematical ideas, whatever we will call it. If you have any question, please ask me. There's very few participants left, but whoever left, please, if you have any remark or anything, please. Ryan, if you have anything, every time you try to prove different things. So do you like how this Euler solved this problem? This type of proof thing does not occurs before Euler's. Euler से पहले ये technique किसी ने नहीं use की थी इस तरीके से notations use करके, and then he relate one thing with the other thing and then solve the problem.
Yes, Hoyle is well known for being very good mathematician.
Yeah, he's a very good mathematician. Do you people know any other thing related to Euler?
to the I pi plus 1 equals 0.
Yeah,
This identity.
this identity is proposed by Euler. And people say this is the most beautiful identity in mathematics. Okay, anybody else? Okay, if you do not have anything, so let's finish here.